The next talk will be by Hsin-Chieh Liao about equivariant gamma positivity in Chow rings and augmented Chow rings of matroids.
So first, I want to thank the organizers for putting up such a nice event, and also the opportunity for letting me speak here. Is my voice loud enough? Okay. So yeah, so my topic is about the equivariant gamma positivity of Chow ring and augmented Chow ring of matroids. We have seen, well, kind of heard about Chow rings and augmented Chow rings, for example, in the first days, Graham's talk in the first day. So, first, we have a polynomial, degree D polynomial with real coefficients, and we say the polynomial f of t is palindromic if its coefficients satisfy this condition, though the first is equal to the last one, and a1 is equal to ad minus 1, then we will say this is a palindromic polynomial. And we say it is unimodal if we look at the coefficient, it's just increasing at some point and then keep decreasing. That's what we call the polynomial is unimodal. And when we have a palindromic polynomial, this f of t can be uniquely expressed in terms of this form. This is usually called the gamma expansion of your polynomial. And the coefficient gamma k here, this is usually called the gamma vector, which will be mentioned in the talk later today. Yeah, and if you are the coefficient inside the expansion of all the coefficients are all non-negative, then we usually call this polynomial as gamma positive or gamma non-negative. So for example, so this is a palindromic polynomial. You can see the coefficient is kind of symmetric and it's unimodal. And we say it's gamma positive. Basically what we do is just, okay, we look at the coefficient of this thing and then we try to remove the row of Pascal triangles from these as many times as you can. So like if you look at these, the first thing you can remove is just 1, 4, 6, 4, 1. And then you've got these things. And then you can remove 1, 2, 1, like 22 of them. And then you've got these. And the coefficient you get is just 1, 22, and 16, which is right here. And if they are all positive, then we call this is polynomial is gamma positive. Yeah. And so why do we care about this? First is, well, this gamma positive of, so in the space of palindromic polynomial, gamma positive actually lies in the concept between the polynomial's real rootedness and real rooted and also unimodal. Well, you can more refine these concepts, but so this is this is a proposition kind of summarized from the paper by Gels and Brandon, and this is stated in Ferroni, Nelson, and Vacchi's their papers, saying that if you have a gamma expansion of your f, and if you take the coefficient of gamma expansion and make up this polynomial, then this new polynomial is real rooted if and only if your original polynomial is real rooted, and this will imply gamma positive and then imply unimodality. So it lies kind of in the middle. And another reason is that actually there are many examples of palindromic polynomial that the gamma vectors are counting by very interesting combinatorial objects. For example, so this polynomial is actually known as the Eulerian polynomial when n equal to 5, and the coefficients are actually counting some subset of permutations. Like it's a subset of permutations with number of descent, and the descents should not be consecutive, something like that. Yeah. So they are counting by some interesting combinatorial objects. And the last reason is kind of these gamma positivity result kind of related to a big conjecture in discrete geometry called the Gauss conjecture. It says that if we consider the H polynomial of a simplicial sphere, and it is gamma positive if the simplicial sphere satisfies some geometric concept called like its flag. Yeah. And well, so this is kind of about the gamma positivity. What does that mean? And so our main character is this Chow ring of Matroid. And this is introduced by Fechner and Svinsky in 2004. So given a loopless matroid M on the ground set E, and this M has rank R, then the Chow ring of matroid is defined as the following. So it's a polynomial ring. Here I'm using coefficient R, but you can use like Q or Z. But so it is a polynomial ring whose variables are indexed by the lattice of the flat in lattice of flats. And then you're modding out two ideals I and J, where this I is actually the Stanley Reisner ideal of the Bergman fan mentioned yesterday. And J is just some linear form. So in Gremlin's talk, he mentioned there are some algebraic geometry background here, but you can just see this can be defined purely combinatorially. And Adiposito, He, and Katz in 2015, in their seminal paper, they show that these Chow ring of matroids satisfy the so-called Kähler package, which includes the Poincare duality, Harlap-Stress theorem, and Hodge-Riemann's relation. Here I will not describe like the explicit, what does the statement for these properties means, but it also mentioned in Graham's talk in the first day. But what we care about is, okay, if we consider the Hilbert series of the Chow ring, which is defined the following way, you're counting basically it's a generating function of the dimension of each graded piece. Well, then the Poincare duality basically means the palindromicity of the Hilbert series, and Harlap just means the unimodality of the Hilbert series. So natural question is like, okay, so how about this gamma positivity? And this is proved by Ferroni, Mathan, Stephen Vacchi, and independently by Wang in 2022. But what they're using is something called the semi-small decomposition of Chow ring introduced by Brandon, He, Mathan, Proudfoot, and Wang. And this will give them kind of like a recursive argument to show that it is gamma positive. But we know the coefficient is a positive integers, and there was no interpretation for these integers in the result. Yeah, and in my title, we talk about equivariant gamma positive. So what does it mean? So now we have a Chow ring, and we consider a subgroup of automorphism group of your matroid, and that it will act on the lattice of flat of your matroid, so it will induce inside action on each of the graded piece of your Chow ring by just, you look at a monomial, they were just like, okay, permuted the index in monomial. And this will give your Chow ring graded pieces CG module structure. Oh, and these AI, the C here just means that we extended the coefficient to a complex field. And now we can consider something called equivariant Hilbert series. So in the Hilbert series, we're looking at a generating function. The coefficient is just a dimension of the graded piece. But in the equivariant cases, this is, we change these coefficient to be the isomorphism class in the representation ring of G, whose the representation is exactly carried by these graded piece. Or you can also think of these as just, say, the character of G corresponding to this representation. And so it will be a polynomial ring whose coefficients are inside this representation ring of G. And Angeron, Nathanson, and Reiner in 2023, they conjectured that, okay, this Hilbert, equivariant Hilbert series, when you also do this gamma expansion, and then the coefficient gamma I here, now it will be some addition, subtraction inside these representation ring, or think of it as additional subtraction of the character of your group. So in general, it could just be some class function. It doesn't need to come from some character of G, but they conjecture that, okay, this gamma I is actually a genuine representation of G. So it's really a character coming from a representation. And this is what we call the equivariant gamma positive. Okay. So in this talk, I will kind of describe how we prove this conjecture. And the proof is, in some sense, I think it's kind of elementary. Yeah. Okay. Any questions so far? Okay. So, the first thing what we use is this Chow ring of Matroid as a CG module. It actually has permutation basis. So this is a theorem, summarize a theorem from Fechner, Izvinsky, and Angro-Nathanson, and Reiner. So Fechner, Izvinsky, they show that this Chow ring has a basis, this basis, and this is coming from a Grobner basis of the ideal I plus J. And in the literatures, usually in some special case of matroids, like people notice that these bases are permutation basis in some special matroid case. But I think kind of Anthony, Nathanson, and Reiner, they are the first one really write out explicitly, like, oh, in general, this is always a permutation basis for any matroid and for any automorphism group action. Yeah. So okay, so they will have this Chow ring will have a monomial basis, and these monomial bases are indexed by chance inside your lattice of flats, and their exponent kind of has some restriction here. So this is an example for the Boolean matroid when n equal to 8, and this is a basis element. So basically, it says that if you're looking at a chain, corresponding chain, the first flat in the chain, it need to have rank at least 2. It couldn't have just rank 1. And then for 2 consecutive chains, their rank differences also need to be at least 2. And then the exponents should be less than or equal to the rank difference of these 2 consecutive flats minus 1. So this is the rank of this thing is 7, this is 4. So the exponent here can be either 1 or 2 or 0. Yeah. And when n equal to 4, these are the basis elements. We separated in degree 0, 1, 2, and 3. And you can see these bases are invariant under S4 action. And you can see, like, okay, these 6 elements forms a permutation basis, and these forms a permutation basis. And 1, 2, 3, 4 itself forms a permutation basis. So, so you can kind of see from these examples that each graded piece is actually isomorphic to a direct sum of permutation representation generated by chance in the lattice of flat with a fixed rank set. Yeah. So here we denote the permutation representation generated by the rank set S. And S will be a subset of a set 1, 2 to R minus 1 if your rank is R. And we will use this notation to denote these permutation representation. Yeah. Oh. Yeah. And so basically, you look at here, for example, in here, these forms a permutation representation indexed by 2 and 4 because this is rank 2 and rank 4. But if you see that if you have 4 here, like 1, 2, 3, 4, when you use S4 act on it, basically it's just kind of act trivially. So this is also just isomorphic to 2. So when you have 4 in the when you have rank R in the index, you can always remove R. So it will just be a subset from 1 to R minus 1. Yeah. So so what we need to know is kind of like, okay, now, oops. We know there are always the direct sum of these kind of permutation representations. So what are their multiplicity? And if you fix a subset in 1 through R minus 1 set, then the monomials that contribute to these permutation representations are in this set. And basically, you can kind of write it out nicely. So they are just chains here. And then each of these exponents has these kind of restriction. And you can just write out the coefficient by just reading this the exponent. So the exponent here just means that it will just represent by t plus t squared to t to this thing. And we can express it in this way, where this nt just means you're summing from 1 plus t to the n minus 1. And then these can be written in this way. And therefore, if we write out the equivariant Hilbert series, each of the coefficient, this polynomial of the permutation representation, can be written in form like this. And, oops, sorry. And you'll kind of notice that this polynomial is non-vanishing only when your subset S, so S is S1, S2 to SL, the subset S lies in the set 2, 3, 4 to R minus 1, and it contains no consecutive integers. Yeah, and so such a subset, we just write it as stab 2R minus 1. So we can write our Hilbert series in this form and run over all the subset in 2 to R minus 1 that has no consecutive integers. And there's a reason why we use this notation. So in poset topology, if you count the dimensions of these things, we are counting the number of chains with a fixed rank set, and this is also known as the flag F vector of your poset. And what we do is, okay, we consider a virtual representation, which is defined by using this alpha, this permutation representation in this way. And when you count the dimension in poset topology, this thing is actually something called the flag H vector, but now we're kind of configure also the group action on it. And so by the principle of inclusion-exclusion, this also has equivariant, the beta thing can also be, the permutation representation can be rewritten as a sum of these beta for all the subset in S. And well, a theorem by Stanley says that these virtual representation is actually genuine, and this is isomorphic to a top reduced homology of some subposet of lattice of flats. So this is a rank selected subposet of Lm. So this just means, LMS, this just means that you're looking at your lattice of flats, you preserve the top and the bottom element, and you remove all of the layers whose ranks are not in S. And then turns out the gamma coefficient as a representation is just isomorphic to this top reduced homology. Yeah. And so, okay, so we can change this alpha into this beta and then make it into the form like this. And okay, so what now we have this kind of weird sum. You are summing. So for any this beta with a fixed t, we're summing all the subset S that contains t, but it also has no consecutive integers inside. And what is this thing? It's kind of surprising. Just like this kind of weird sum is exactly equal to this. Yeah. So when your t, yeah, it's just equal. Yeah, and we will show it later. But from here, we basically just found, okay, so the gamma expansion for the equivariant Hilbert series is just these things. Yeah. So the proof is kind of just, I think it's kind of elementary. And also, if this can also reduce to usual gamma positivity by just counting the dimension. And in this case, the dimension of these things is just the Mobius function of this rank selected subposet with some sign twist. Okay. Any questions so far? Okay. And so now, so how do we really prove this identity? Okay, so basically I'll kind of just show this by just an example. We're using some combinatorial model. So For example, when our R is 12, and when our subset S is just 3 and 7, so these polynomial can be written this way, and when you expand it, it's basically a product of these things. And we can think of this as like counting some sequence. So this is when R equal to 2, we're counting the sequence of length 11, and this sequence has alphabet over something like circle, cross, and then the empty set. And what we do is, okay, so the set is 3 and 7, so we put circle in 3 and 7. And then this t plus t squared basically just means, okay, we can either put a cross here, or we can put 2 cross, and this represents t plus t squared. So we're just counting such sequence and the number of these crossing. So for example, the second one, these things, you can put just 1 cross, or consecutive 2 cross, or 3 cross, they give you these things. And in the end, you will have either no cross, 1 cross, and then 4 crossing. And so you are just counting the crossing over such subsequence, and this will give you these polynomial. And one thing to notice is whenever you have this circle, you will always have a cross first. And so in general, if R is these things, T is still same. So what we want to show is these. But okay, so according to what we mentioned, what does these sum count? This is actually counting sum over all the sequence of length 11, and then the circle appears at least at position 3 and 7. This is counting on the left-hand side, yeah. But we can also compute these things in another way. So another way is we already know we have length 11, and we have circle in 3 and 7, so we put 3 and 7 here, and then this always come with this crossing here. And this cross already give you t squared, which is actually these things. And then what we need to do is now there are 7 remaining positions. We can either choose to put cross or not cross. And this will give you either 1 plus t to the 7, which is these things. And it turns out that when you do this, you just put any cross you want, and then there's always a unique way you can just put put the circle after each cross, and then they will give you the sequence you want. And so this tells you that these two things are equal. Yeah. And that's, yeah, so this these show these results. Yeah, I think this kind of non-trivial why this is true. Yeah. Yeah, and so that's for Chow ring, and there is also an extension of the Chow ring called the augmented Chow ring of Matroid. So in 2022, Ha and Larson, and independently by myself, we found a basis for these augmented Chow ring, which is very similar to the Fachner-Zvinsky basis for Chow ring. And the only difference is just like the first exponent. Yeah, and turns out this also is a permutation basis, and we can do the similar stuff. And so a proof similar to the non-augmented cases also works for the augmented Chow ring. And we will have, so this will be the gamma positivity for the augmented Chow ring. The difference is here, now instead of consider the consecutive subset in 2 to R minus 1, we're from R to 1 to all the subset from in 1 to 2 to R minus 1. And then in the Chow ring case, this is R minus 1, but in the augmented Chow ring, this is R. Yeah, and that's all I want to say. Thanks for your attention.
Okay, thank you very much. Are there any questions? If not, then we'll take, yes.
So at the very end, first of your talks, you say that this the real rooted implies the gamma positivity and the unimodality. So I remember that real rooted also implies the log concavity. So what is the relation between the log concavity and the gamma positivity?
Yeah, so go back. Yeah, so There are actually like more refined concept. There's like Polyar frequency things. You can the polynomial is real rooted. I think is equivalent to say it, if only if it is the sequence of the coefficient is like PF, and there's like PF1, PF2, PF3, and I think the gamma positivity is the PF2 will equivalent to what is that, the ultra low concavity or something. I forgot the name. Yeah, but PF2 implies these low concavity result, and then implies gamma positive and implies PF1. Yeah.
I don't know if this is particularly helpful, but I think I've seen something about this in Peterson's book on Eulerian numbers, and the relation between these positivity properties is slightly awkward. Namely, you have this, like, you can make this Venn diagram of gamma positivity, lock concavity, and real rootedness somewhere inside the intersection, but there are things that lie outside, so it's not really an inclusion, so it's a little weird.
Okay, thank you. If you have other questions, please save them for the coffee break, and we'll now take a 15-minute break and meet here again at 5 to 11.